Good morning. Last lecture till spring break, right? So it's good. Okay, so today we're going to do some more advanced op-amp based circuit architectures, but also show you that pretty quickly when you're doing op-amp circuits, you won't even be doing nodal or KVL, KCL, but be able actually to solve these circuits by inspection. Right? And they will get bigger and bigger, but you'll be able to recognize kind of the blocks, just like we did with resistive dividers, voltage dividers, current dividers, parallel series resistors. Now there are larger blocks that you can recognize by function and just use to create what we call analog signal processing. In fact, just in discussions after this, you already start doing that, essentially putting together larger functions by recognizing kind of op-amp building blocks as components. An inverting amplifier, non-inverting amplifier, a buffer, a summer, etc., right? And so then as you think how signals flow, what you want to do at the design problem level, you'll be using these blocks as composables. Say, I want to add two numbers. Oh, there's this topology for a summing amplifier, right? So I'm going to use that and then think what it does to the rest of the circuit, rather than go and write out detail, 10-node nodal analysis for the whole thing. Okay? But one step at a time. So we're going to start just revisiting a little bit the inverting structure. Resistor here. Okay, so there are a few things here that we did last time that may have not gotten across quite right. We're going to be using, for the sources, this squiggle is just with the reference sign. I mean, you can write a minus, I'm just lazy. And we also label them as lowercase. The reason is that, as I showed you earlier with DACs, right, we have interest in passing signals that actually change in time, like playing music from a speaker into a speaker or some control signal or whatever, through this system and doing something to it. So hooking up a DC supply here is not really interesting, okay? So this will be a signal that changes in time. Everything that we've shown you, like the ideal model of the op-amp is just voltage-controlled voltage source. The voltage gets changed instantaneously at its output depending on the input. So there's no delay in this system, basically, right? So that's why I can immediately say that as the input changes, the output will change that very instant. And I will also keep the output as lowercase. Right? Okay. Usually, this V in will be coming from some other circuit, right? So I'm not just going to be putting it as V in, but like some V in or Thevenin or some source resistance, simply because that circuit, any circuit, as we know, can be modeled as a Thevenin source and a Thevenin resistor, right? And you'll see some of that today too. Okay. So let's analyze. The goal is always to figure out, okay, V out as some function of V in. What is it, right? I want to figure out what this circuit does to this input signal. How does it transform it all the way to the output? So this will be some form of a gain here, because that's kind of all these circuits do pretty much. Okay. So I can go now and apply some equivalences or some Ohm's law, KVL, KCL. But if you don't know where to start from, early on, probably it's easier to just do nodal. Okay. So we'll have this node here. It's called B. And it's a single nodal equation you need to write. Okay, who can tell me what will be the terms? I'll just label the flows. There's 3 flows. Okay. So for this term, what do we have? for the left. Don't worry yet about knowing whether golden rules apply or not. You don't need any of that. Yes?
For that one, it's negative V in over R1.
Okay, so you're saying negative V in over R1. You jumped a few steps. So I just want to do like very vanilla nodal. There's a potential in this node. The potential is VB, or we can call it, or potential to voltage to ground, or potential in this node is VB or V minus, right? But we're just going to do it from the perspective of node B. So just for this branch, normal nodal. Don't worry about anything else in the circuit. Yes?
V minus Vn over R1.
Yes. So it's VB minus Vin. And then you can, whatever, we'll write it as over R1. You can also say G1 like we did before. That's okay. Anyway. Okay, so this is our first flow. What is the second flow? The one that goes up. Again, just look at the element on the branch, right? Okay. R2. Okay. What is the third element? The one that goes into the op-amp. 0, right? It's I minus. I'll just write it as I minus. That equals to 0. So let's take a look at some of these. For me, I couldn't have said 0 here without applying some rule, right? I don't know actually what that is. I'll just write it as I minus here. And then I'm going to apply some rules. So by Gordon rule number 1, I plus equals I minus equals 0, right? So that always applies for op-amps. And so this will be 0. Then, to figure out what VB is, I need to apply golden rule number 2. Okay? So I need to check whether this circuit is in negative feedback. If we null this source, increase the voltage here, this voltage would increase, and since it's on the negative sign, the increase in that will decrease the error, so the output will decrease. So okay, it is negative feedback. Right. In general, you can kind of check negative feedback fast if the feedback element is just a passive element, a resistor, a capacitor. If you're connected to a negative, that is negative feedback. Right. So you don't even need to check that. But I'll show you later the case where that's not the case. If you put an active element in the feedback, things can change, right? But by a passive element, I mean an R, resistor, or capacitor, right? They will not change the sign of the signal coming back. So, okay, so we have negative feedback, and from it, we can apply golden rule number 2, which is that V plus equals V minus. In this case, V plus is 0, right? So V plus is 0, and therefore V minus, which is VB, equals 0. Okay, so I can go now here and say this is 0. Okay, so what do we get? We get minus V in over R1 minus V out over R2 equals 0. Okay. If now we move V out on the other side, we get V out over R2 equals minus V in over R1, or V out equals minus R2 over R1 times V in. Right, that's it. So only one, yes?
Doesn't this result mean that the voltage is
Voltage is heading towards the op amp. So V out is the voltage between the output terminal and ground, right? All this means is that if V in is positive and increases, V out is negative and decreases, right? So yes, how do you produce a negative voltage? Well, we said that op amps can have positive and negative supplies, right? And can handle anything in a range you give it, right? So we're always here assuming if we don't draw the supplies that the input signal and the output will be within the range of what an op amp can produce before hitting one of the rails, right? It is up to you once you derive this to check that, right? When you derive this, and if you know the range of the input, let's say we know input is plus minus 1 volt, and I know what these two components are, I can figure out what is the range of the output. If the range of the output is larger than the supplies, then this is not going to work. So sometimes you'll be asked even to set the gain based on the input range so that you hit the output range. For example, let's say here V in is in the range of, plus minus 1 volt. Right? Well, let's write it better. We in from minus 1 to plus 1, right? Volt. So it's in the whole that range. I need to set R2 and R1 such that I fully amplify to V out range of minus 3 to 3 volts. Right. So what should R2 and R1 be? So I want this signal, which is plus minus 1 volt, to be amplified. So from input minus 1 volt to plus 1 volt, this is V in. I want this amplified to plus 3 volts, minus 3 volts, V out. Right. This block in the middle is our whole inverting amplifier. Right. So what are R2 and R1? Why don't you talk a little bit among yourselves? Figure it out. Yes? Ah, you mean negative feedback? Okay. So if we increase, so we null the source. Nulling the source means a short. You increase the output. If this is shorted, there's zero current flowing here, right? Because that's I minus is 0. You just have two resistors in series. You're increasing this side. By voltage divider, this voltage increases also. Right? There's the equivalent model for that is basically this. R2, R1, node B. This is ground. This is V out. Right? So if this increases, this of course must increase. Right? And then if that increases the negative terminal. Right? So you have 0, and the negative terminal increases, so the error decreases. you're amplifying here that error, right? So now you're amplifying a smaller quantity, so the voltage drops. Right? Okay, anyone figured out what these two values should be? Yeah, so we want the gain here to have magnitude of 3 because we're amplifying from 1 to 3, right? So R2 will be 3R1. Now, the gain will be how much? Negative 3, right? So we're going to sometimes label that, and in the reader I think it's labeled like AV. This is not the A that's inside our op-amp, which is ginormous. That's why we put this V here. It's voltage gain here, right? So voltage gain of this op-amp is minus R2 over R1, or is equal to V. Okay, let me just define this better. Other slide. So AV, this is voltage gain of by amplifier here we mean a system, not an op-amp. Our amplifier here is the whole thing, in this case inverting amplifier. So this is V out over V in. And in our case here, it's minus R2 over R1. Right? That's just for this case, for the inverting amplifier. For inverting amplifier. Right. Okay. So what that would mean is if I have a minus 1 volt input, it will actually become a 3 volt output. Right. If I have a 1 volt input, it will become a minus 3 volt output. Right. And anything in between, right? Does that make sense? Yes?
Does music sound different on a speaker if it's positive or negative, like the sign is changed?
Well, music are waves, right? So you will actually always want to, if you think about the music as being composed out of notes, right? And with the drums, you saw that each note is basically a mode, right? It's actually a sinusoidal signal, right? It's some frequency. Each tone is some frequency, and frequency is an oscillation that always basically goes up and down, right? That's what happens in the drums. The only things that remain for you to hear once you hit the drum is the mode. That's the oscillation that persists in that oscillator, right? Yes?
You said earlier that a passive element in feedback won't change the sign of something. What are you talking about?
So I was basically saying that this is a passive element, R. Sometimes, very shortly, you'll see that we'll have C's as well. If you have just that element or a set of elements like that in the feedback path connecting output to the negative input terminal of the op-amp, that terminal has to be negative in order to retain negative feedback. Right? Simply because if you see this scenario, whatever I have here, some equivalent resistor capacitor or some equivalent resistor capacitor, I will always get some form of a divider here. So if I'm increasing the output voltage, this node will have to increase. Now, if I have an active block, like another amplifier, that we're going to do shortly, this is not true, right? But a quick inspection is, if you don't want to do dink and move around the circuit, boom, you have a circuit with resistor. In the feedback, you know it has to be hooked up to the negative terminal. Okay. Okay. We can do, okay, so one other thing, actually, while we're here. This circuit that we just did some kind of signal processing on this input signal. It amplified it and inverted the sign. right? So it amplified by a factor of R2 over R1 and inverted the sign. So when we think about it as a building block, the moment we see this topology, we no longer have to solve it. We know immediately what it does, what its transfer function is, right? So we can write it as a block. This will mean it's a gain of minus R2 over R1. Right. Now, there is one caveat here, okay? And that is that if I want to use these blocks to compose larger functions, I would not want one block to load another block. I want them to basically operate independently. What do I mean by that? Well, take a look here. This circuit starts with a resistor, right? And there is actually some current flowing from this supply right now, or a signal source, but it could be another circuit, into this circuit. That is called loading. Depending on what the value of this resistor is, that will change the value of this current. Right? This current is V in over R1, right? Well, that's not good, because that means if I have some circuit in front of this circuit, the amount of current it needs to provide that will depend on my choice of R1 and R2 here. And I could have had the same exact gain, but had a smaller R, and that would change the result. Right. Think about the previous circuit being a simple V Thevenin, R Thevenin, right? Right? If I now add my inverting amplifier, what is now, so this was supposed to be my signal over here, right? This was the boundary between the two circuits. Right? So I wanted this voltage to be my V in. But look at this right now. V in will now be this voltage minus, will be essentially, we can do it because it's 0 here, it's a voltage divider between R and R Thevenin. Right? So V in will be R1 over R1 plus R Thevenin times V Thevenin. This obviously depends on R1. So this whole composability now breaks. I just wanted to be able to add this circuit without disturbing this circuit. By disturbing means that V Thevenin would all show up here, and there will be no current flowing. Right? So what circuit do we know that we can add here to save the day? I want to isolate this V Thevenin, R Thevenin from the inverting without changing any total calculation. Right? Just want to put something here that creates a 0 current here, but replicates the voltage. Capacitor is not going to work for any AC coupled, which is beyond kind of what we're talking about here, is going to work only for some frequencies, but not always. Right? There was, yes? A buffer, that's right. So what we're going to do here, we put a buffer. So now, okay, I've got to redraw it a little bit, sorry. Okay, so this is a buffer. We feed back to the negative port. Feed here the positive port. There is 0 current flowing here because that's I plus. Okay. So V plus here equals V Thevenin. And then V in equals V plus. Because this is a buffer, right? We did that. The transfer function for this buffer is basically whatever is at the plus terminal, that voltage it passes through, right? We did it last lecture. So this now, if I now make this my block, then I can take this block and attach it, put it anywhere in the circuit. And it will just sense the voltage without disrupting this previous circuit. And it will produce V out regardless of what the load is. So can anyone tell me why can it produce a given V out? V out here will be always minus R2 over R1 V in, regardless of R load. Why is that the case? Yes?
Is it because by golden rule number 1, it's like thinking of voltmeter as VR, right? There's no current going to RL.
Are you talking about input or output? Well, you're not sticking any voltmeter at the output. There's another element that guarantees this. Think about what's the equivalent model of the op-amp. What drives the output of the op-amp? Yes? Yeah, A times V error, right? The voltage-controlled voltage source. Well, voltage-controlled voltage source doesn't care what load it gets loaded with, right? Whatever current it needs to supply just happily supplies it, right? As long as it enforces the desired voltage, right? Therefore, the output that this op-amp will produce is not going to depend on anything you attach to it. Right? You can attach 1 kilo ohm, 1 ohm, whatever. That's what we did. That's how we were able to drive the loudspeaker last time, because op-amp can provide enough current drive, even into a few ohms of resistance. Does it make sense? So the key concepts here are, there's isolation here. The fact that input current equals 0. That's isolation. So now this block from its input standpoint looks like a voltmeter, right? Because it just goes, measures whatever's coming at it without sucking any current from that circuit, right? And without changing that voltage. It's kind of like Heisenberg's principle, you know? You want to kind of measure something without disturbing it, right? So you want to attach this circuit to the circuit before it without disturbing this voltage, right? So you have to do that by not sucking any current here. Because if you take any current here, the voltage here at the input will change because of this R Thevenin. Every circuit before that has some R Thevenin. Does that make sense? So this is one of the key principles. When you start composing bigger circuits, you will want the follow-on circuit to not load the previous circuit. Right? And then, if you have an output, in this case, you can afford, if I was composing, let's say, another block like this, with this op-amp output, I can drive anything. I could drive even directly this inverting amplifier, simply because here I don't care what the load is. I have a voltage source driving the load directly. Here I didn't know what my previous block is. Right? If it had some serious resistance with it, then I need to isolate. Right? If it's just an ideal voltage source, I don't need to isolate. Right? Because the voltage source will just keep its voltage across. Okay. Does that make sense? Ask questions? Yes? Have I done? What if I use a non-inverting? Yes, great question. So let's revisit that. right? So this is the full picture, right? I have this is previous circuit. So there's some circuit. I'm attaching an op-amp, non-inverting op-amp on it. The voltage here to ground is Vin, right? Because this is my non-inverting op-amp block. What was the gain of this one? V out to V in. Does anyone remember? Okay, it's the other way around, but you're close. It's 1 plus R2 over R1. Simply because V in is the same as this potential, right? So then the current that flows through here is V in over R1. Then this voltage, no current flows here, so this voltage is then V in over R1 times R2 over R1. Okay, so this is the gain. Since I'm driving the load straight from the op-amp, right, I don't care what the load is. This will always be the transfer function. The input, does it load the previous circuit? What is V in with respect to V Thevenin? I have V Thevenin, R Thevenin going straight into the plus terminal. So what is V plus? Why? Yeah, so this current is 0. So the current through the resistor is 0, so the voltage across the resistor is 0. Right? So then V Thevenin equals V in. I'm not loading this whole circuit with this. So this is fine. This one does not need a buffer because you're feeding, you have isolation here, right, with 0 current, just like we had here. Okay. Now, notice one thing in this composition. I had a buffer driving R1. Why was this okay? Yeah, I'm not drawing any current here. But how did I know that putting R1 here doesn't change the function of this buffer? It's a voltage source. This buffer, if I look at it as a circuit, has 0 Thevenin resistance. It's just a voltage source, right? So therefore, I can basically load any load to it. It's okay. There was a hand. You? No? Okay. Okay, so let's do a few more circuits. Or actually, let's solve, let me see how much time do we have. I'm going to solve this one with superposition too. Okay, good. So this is nodal. The more you're familiar with KVL, KCL, equivalences, and superposition, you can kind of also analyze these circuits with somewhat of a shortcut, right? So let's try to do that here quickly. Don't worry if you can't do it yet, but try a few times. So if I have a circuit like this, I can basically, again, go and say, hey, this circuit is in negative feedback, this voltage is 0, therefore this voltage must be 0. This voltage is 0, then the current will be V in over R1, going this way, because there's V in across the resistor. That current has nowhere else to go because there's 0 current here, but this way. Right? And since V in over R1 is flowing here, the voltage that it realizes across is V in R2 over R1, but it starts from 0 and pushes down. So then this is minus R2 over R1 Vn. Right. So that's kind of a quick way without writing any nodal. I sort of did the nodal as I went along, but it was a faster way. Okay. Let's have another example that looks like this, but will require an extra technique to do it. Okay. Okay, here's the circuit. So who can tell me what should the polarity be of the op-amp so that this circuit is in negative feedback? Okay. So you could go and say, oh, there's just a resistor in the feedback, like, so that's valid. The other one is, again, null the sources, increase the output, and then look in the feedback. So you get R. There's no current here. You just get two resistors in parallel to ground. It's a very similar thing to that divider. It's now a voltage divider between R3 and R1 in parallel with R2. Right? So again, if this goes up, this will go up. Again, you're squishing the negative terminal toward the positive, so this goes down. Okay, so this circuit is in negative feedback. Now, we can still name this node B. Okay? So why don't you talk to your partners for like 30 seconds, work out the nodal for node B. Okay? First term, what is it? Yes? Okay, so let's do the one, like the basic. Okay? S1. Okay. Second term. Anyone else? Second term, the one down from B to VS2. Okay, let me just make sure these are small. Yeah. Over? Mm-hmm. Okay. Third flow, up. Someone else? Yes? Over R3. Okay, fourth term, easy. Zero. Okay, I minus, right. So I minus is 0. Because of negative feedback, this is GR2. V minus equals V plus. So V minus is VB. This V plus is 0. So VB is 0. All right, so we'll say this is 0. And we get that V out over R3 equals, I'm going to label this in S1 and in S2, so like input signal. It's not a supply. Equals minus V in S1 over R1 minus V in S2 over R2. If I multiply everything by R3, I get that V out equals minus R3 over R1, V in S1 minus R3 over R2, V in S2. Yes?
So this is what you would have got for superposition, right?
Yes, I was just about to ask that question. So really good observation. Look at these two terms, right? If you look at just this term, what does it remind you of? Just this term. Minus resistance in feedback over the feeding resistor times V in. What circuit does that remind you of? Non-inverting amplifier, right? We just did it at the first half of the class, right? So if you think about this circuit, even topologically, when you look at it, if I forget this branch, it looks like an inverting amplifier. If I forget this branch, it looks like another inverting amplifier, right? So the result sort of makes sense, but let's see how we can actually apply superposition to confirm that, right? What happens with this circuit if I null V in S2? So let's redraw it. Okay, and I have here I've shorted V in S2, right? So it's gone. And now I'm looking at this circuit, and let's see what happens. We know what's the voltage here in node B, right? So 0. So there's 0 here, there's 0 on this side, right? Ground is on this side. What's the current through R2? 0, right? So the current is 0. So the current is 0, I can just ignore the whole branch, right? It's like it doesn't exist. Yes?
Actually, are we sure the current there is 0? It looks like there could be a volt.
Well, the potential on this side is 0. So I have an R2 as an element, right? I have 0 volts on this side, 0 volts on this side, right? So these are the two potentials, right? So what voltage difference is 0 minus 0, right? So the current is 0. voltage is 0 volts. Okay. It's 0, so it's like I can delete it. It's like it doesn't exist. It doesn't load this circuit at all. Right? And so what is this circuit now that you see it like this? What can you immediately, without solving anything, write for V out 1? Negative R3 over R1 V in S1. Right? We just said, from this moment on, when you see this topology, you just write this. You don't go writing KVL, KCL, nodal. There's no need to. It's just like rederiving voltage divider a millionth time, right? So don't do that. You're wasting your time. Just remember this, okay? There's only a few of these topologies, and then that's it. Right? Okay? So what about the other case? We have this one is shorted. We have R1 here. We have R2. R3. V out 2. The reason why I'm putting indices here, out 1 and out 2, is because that's in response to a source. I'm doing superposition, right? Okay, so again, what's the voltage here? At this node, B. 0. What is the circuit current in this branch? So yeah, this current is 0, so I can basically delete this whole thing. Now, I get again an inverting amplifier. So what is V out 2? R3 over R2, V in S2. So that's basically this piece. And what we derived here was that first piece. So V out equals V out 1 plus V out 2. Right. Okay, so this is superposition. Now, this all depends. So what is easier? Is the nodal easier for you? Nodal was not that complicated in this case, right? But hopefully in time, you'll be able to do this quickly. Just null the source, simplify again the topology, see that this topology is something you recognize immediately what it is, and just write the formula, right? Rather than going to nodal. Op-amp circuits are not going to become very complex nodal circuits. You will at most have like 2 nodes to solve, but pretty much 1 node most of the time. So you can go down that route, it's just gonna take you time, and you're losing insight. This way, you kind of see kind of what the circuit does immediately, right? And that helps you compose circuits more efficiently. Okay. Let me see how much time do we have. Okay, good. Okay, so let's try this circuit. Okay, so here's the circuit. One of the things to figure out is the polarity so that both of these things are in negative feedback, right? But what observation can you make by just looking at this? I mean, we can go and solve it through nodal, okay, once we figure out the polarities. But in order to do that, yes? Overall, it seems like it's an inverter. Sure, but like it's kind of hard to say without trying to decompose things, right? So what would this block look like? Yeah, so this is the feedback block. If you think about like how we did our feedback, it was the A block, right? And then was the F block that fed back. There was some essentially plus minus here, right? So this whole thing over here is the F block, the feedback block. Do you recognize that circuit? It's an inverting amplifier, right? Just that we just did this lecture, right? So when you approach these circuits, that's exactly how you should think. Think about building blocks. What building blocks does it consist of? Can you recognize them? Can you apply already some things that you know about it? So if we just look at this block, let's say we'll label this node A and this node B, and we look at this block in isolation. VA here is our input. VB here is our output, right? How should in order for this block itself to be negative feedback, because then I know its behavior, what should the polarity be here? Okay, so negative and positive, right? So this polarity is because I want it to operate in this known fashion, as an inverting amplifier. So if that's true, what is VB? Let's label these as R2, R1. What can I write for VB immediately? I'm still assuming, I'm assuming a situation like this, that these two circuits are not connected. Just analyzing this circuit at the bottom. Yeah, VB is negative R2 over R1 VA. Yeah. Does anything change in this circuit if I make this connection? Why? Well, first of all, the current is 0. Second, I'm driving from a voltage source. I don't really care, right? It could be some load, resistor, whatever. I'm just going to still enforce VB that follows this, right? Okay. Here, I need to be a little bit more careful, right? And look what is actually driving this node VA. If it was a V Thevenin with R Thevenin, I'd be in trouble, okay? I would need to put this buffer to isolate. But if we look at this is actually an op-amp, so it is an ideal source. So whatever V out it's trying to drive, when I hook it up here, that V out will stay, right? So I can make this connection. Yes?
What happens if it's not isolated, like there's an external current?
Then we would need to go back and isolate, right? Put a buffer there, or take into account this drop. But then I would not be able to just say, hey, this block has just this transfer function, right? What I really want to do is instead of this F, right, minus R2 over R1, right? And I want to say that this V out, the output of the feedback circuit at VB, is just minus R2 over R1 times V out. If, however, this circuit is loading this circuit, right, then it will be changing the V out. Like in this case, it's not, because what V out, there's a voltage source here, right, that drives out. And whatever this voltage source says the V out is, this circuit is not going to change that. Does that make sense? because you're forcing it with this voltage source. However, if I had some resistor here, right? Real amplifiers actually do have a resistor there, right? So then it becomes problematic. Yes?
Even if you have a resistor there, current cannot flow there because
Yes, it can. Current here is this. In this situation, if there's no current here, the current flowing here will be this output voltage divided by these two resistors, right? Because there's a 0 volts here.
where would it go?
It would just go up here, just like we did.
Yeah, but it will go to the.
And then here into the op amp, right? It goes here and then into the op amp. The op amp is just a voltage source, right? The current doesn't go here, which is into the next stage. But current will happily flow all the way around here, here, and back into the op amp. Or from the op amp, the other way around, depending on the sign. Yes?
I don't see how adding that resistor there makes the current flow to
Which resistor?
the one you just added.
Oh, even without the resistor, the current flows. The point is that this resistor, if the current flows, and the current is dependent on R1, right, this voltage will also be dependent on that. This was supposed to be your output voltage, right? So if you have just a voltage source, that voltage source dictates what the output voltage is here, regardless of what I'm attaching here, right? Okay, so given that this is a voltage source, and for our course, it will always be output of the op amp is always a voltage source, I can basically just represent this as a circuit where, I have my amplifier block, I have some block that does this. This is my feedback, F, right? Takes V out. This is V in. Right. This signal over here is minus R2 over R1 times V out. This over here is my F factor. Right. So let's take a look at what the polarity should be here. We do that by following the loop. We null the source. If this increases, what happens with this voltage over here? Decreases, right? Because of this sign inversion. So if this decreases, what does the polarity have to be here so that this decreases? So it has to be plus. Right? And then this is a minus. Okay. Then this makes sense? We have inverted the polarity in the feedback loop. Therefore, it's logical we now have to feed the plus port. Right? Previously, if we were not inverting polarity in the feedback loop, we would feed the negative port, just like here. Right? Okay, so now we know that negative feedback is there. And we can apply golden rule number 2. So what does golden rule number 2 say for this op amp? V minus equals to V plus, or in this case, V in. So V minus equals V plus, or V in equals what? Equals this, the feedback signal, minus R2 over R1 V out. So that's basically our solution. Let's rewrite it, just for clarity. So V out is minus R1 over R2 V in. So it's still inverting, but it flipped the R1 and R2. Right. Make sense? Okay. Let's see what else I want to show you. Oh, there are a few that are very cool. So let's do another example. Does this make sense so far? But yes? Oh, you mean at the very beginning of the thing? So, the very beginning, we looked at this circuit, right? This is exactly the inverting amplifier that we did at the beginning of the lecture, right? So I could do it again. Like, you assume that this is the input, right? So the input is nulled. If you increase the output, there's no current flowing here. So this is just a voltage divider of R1, R2. So this voltage has to increase as well. If this voltage increases, and you want the output to decrease, then you have to be on the negative terminal. Why do we want this output to increase? We want to make sure this circuit is stable. Right? It's only stable when it's in negative feedback. Right? It's providing a known gain that we can set by the feedback circuitry. So we're trying to put this one in the polarity such that it is in negative feedback. Right? And therefore, the test for negative feedback is if I change the output, that it comes back as a negative, as the opposite change. Right? Okay. Okay, let's do another example. And this one is going to start relating to the homework as well, probably. Okay. Okay. So let's label these terminals so that they're in the negative feedback. How would you do that? This is now a current source. It's a signal still. There's some current that we're going to be feeding in this circuit that depends on something else. Any ideas about the polarity? Yes?
It should be plus on top because it's like inverted amplifier, except the voltage source is backwards.
So this is a current source.
But you can think of it as like a
Okay, let's try your suggestion. Okay. There's only two ways it can be, right? So you might as well try both and reason about it. Okay, so let's assume it's this, right? And let's try our test. What does this become if I null it? It becomes an open, right? So I'll just delete it here. Now I increase this voltage. What happens with this voltage? First of all, let's take a look. There's zero current flowing in here, right? What current is flowing through R? Zero. That means that this terminal has exactly this potential. So if I'm increasing this, I'm increasing this as well. So if I'm increasing it, but I want to decrease at the output, should this be plus or minus? Minus. Okay. Now think about it. Yes?
So it doesn't matter what direction the current is flowing because you just null it.
Yeah, it doesn't matter what direction the current is flowing, the source current. right? In fact, this source current is changing. It could be positive and negative from the same source, right? It's changing in time. Now, you were right in a sense that this does remind you of the inverting amplifier, right? Think about it. If I had a voltage V here, right? What was the current that was flowing into this node? It was that V in over R1. So I could model that whole thing as this input current, right? If this input current was V in over R1, then the rest behaves exactly the same. Right? That current will be flowing here, going up, and creating a voltage that's a ratio of two resistors. So it is like an inverting amplifier. It's just that I don't have this piece. It's just the current. Yes?
So with the current 1 through R, that can be like the opposite, like negative E and over R?
Well, let's just write KCL for this node B. For B. So what is it? This flow is I in plus this flow is I minus plus this flow is what? Just in terms of nodal, what is this flow? VB minus V out over R3, over R. And that equals 0. This is 0. VB we already know is 0, right? From GR2. Okay? So what we get from this equation is that V out over R is equal to I in. Did I do this right? VB, minus. No, this is I in. Oh, yeah, that's right. I in. Right? Or V out equals R times I in. Right, so think about it this way. I in flows this way. There's no current flowing here. So I in also needs to flow through this resistor that way. Right? So this flow is I in. And then that's V out minus 0 over R. So that gives us this. So this is called a trans-resistance amplifier. Right? Or if you hear a term trans-impedance, that's just a little bit more general term. So V out over I in is R, because the unit of this is ohms, right? We call it trans-resistance. It turns input current into output voltage. You also know this element by another name. Okay? Yeah. Current controlled voltage source. And basically, we said if there's some I in somewhere, we're producing current that is, voltage that is R times I in. Right, that's basically what this thing does. It takes I in from somewhere and measures I in and turns it into voltage. Does that make sense? Okay. So let's do another example, very similar to this one. Okay. So you may have heard the term photodiode, photodetector, something like that. That was actually in your labs used a phototransistor, but it's basically a similar element. You shine it with light, it creates some I-photo, some photocurrent. You have to make sure it is biased correctly, so we don't want to go into those details. Basically, this voltage is 0 volts because of the negative feedback there. It's the same exact example like that one. So I just want to show you that basically you can use these things in practice. This block here, for all intents and purposes, behaves exactly as this block. Right? Where instead of I in, I have I photo coming into the op-amp. Okay? So if I tell you that I photo is the current in this branch, what is V out? Yeah, V out is minus I photo times R. Again, we can kind of write it out, or you can just notice that I photo is the opposite sign of I in, and immediately write it. But we can write it here that minus I photo. This flow is 0, and then this flow is 0 plus 0 minus V out over R equals 0, right? So V out over R equals minus I photo, or V out equals minus I photo times R. Okay, the reason why this is interesting is because depending on the sensitivity of light, or the intensity of light coming into the photodetector, this photocurrent will be changing. Right? So there will be some power of the light coming in, and actually the I photo will be power of the light times something I'm going to call resp, or responsivity. The unit of this is amps per watt. The unit of power is watts. So when you multiply watts with amps per watt, you get amps, right? So responsivity of the detector is just basically how much photocurrent does it give me for a certain amount of power in the light, right? So now I can use this to sense light and then do some action. It's like your automatic dimmer in the room. You want a certain exact conditions, or you want to basically be able to do optical communication like you have in the homework. Right? If I have light that is modulated by on-off, right? So in time, that light looks something like this. So I have P light. This is time. And then I have it at P0, P1 level, and then go down to P0 equals 0. So if I can somehow create a thing like this, right, where I have light, then I don't have, it's like a light switch. Have light, no light, have light, no light, right? Then I could associate the high level of light with a logic 1 and a low level of light with a logic 0. Right? If I then shine that light on this photodetector, I will get the photocurrent that behaves the same way. I have now, this is I photo, will be responsivity times P light, and will behave exactly the same way. And then I'm reading that with my I photo times R, right? So I'm going to be getting V out will be negative, 0, negative, 0, negative, right? This voltage will be minus R times responsivity times P1. Right. Again, it's two distinct levels. What would I need after this? So I could have this basically straight into a comparator, right, and just set the V reference here. Right, so I could go here, put a comparator here. And then how would I hook up the signals here? I need to compare it to some V reference, right? Which is in the middle. So there'll be some voltage here. This now has to be a negative voltage, right? But when the input, this output is less than that reference, I need to get a logic 1, right? That was my original. So I should get a high level at the output of the comparator. So what sign should I use? Over here. When input is less than the reference, I want a high voltage. So is the input on the plus or minus? On minus, right? So in this case, this is our optical receiver. This is a decision circuit. This circuit tells us in logic levels, supply or ground, whether we have sent a 1 or a 0, right? So this is a VDD or ground is the output. Okay, have a great spring break and come back refreshed for the last round.